So we've now looked at the schematic. The next part is looking at the layout. So if you go to File, New, and create a new layout cell, and we create a save space, now you're presented with a layout window. The layout window, you can see it defaults to the transmission libraries because you only have the transmission lines to add, but we are not going to use these predefined components, and instead we're going to draw our own geometry. Of course, if you're working with a more complex design, you can import these from a PCB or an IC design software, which is what most designers tend to use. Before we do anything on the layout window, we are going to choose the grid spacing that we're working with. So everything in the layout will snap to grid. We're using millimeters, so a resolution of about 0.1 millimeter is going to be appropriate and also not too fine, which makes our drawing easier. Now we want to draw a transmission line or a microstrip line, so we'll use the rectangle option. I'm not going to worry too much about getting my drawing exact, so I'll just go and draw a line that looks approximately where I want it to be. So around the cursor, I know that my line wants to be about 100 millimeter long and about 4 millimeter wide for the same dimensions. And now I'm going to go into the properties of the line, and I'm going to adjust these parameters. So I want a width of 100 millimeter, so we can enter that. I want a height of 2 millimeters, and I want this to start at -1. At -1 for the y-axis and at 0 for the x-axis, which means that's now nicely centered. You can see this is automatically mapped to a layer called conductor drawing. We're going to leave it like this, and in order to add our second trace, which is the ground plane, we want to change to a different layer. So having now chosen a different layer, you can see this part went gray, and we will repeat the same process. We will draw what roughly looks like a microstrip line ground plane, and again, we will adjust this to start from 0, and we will give it the same width, or in this case, the length as the microstrip line. And for the height, considering our microstrip line is 2 millimeter high, a good rule of thumb is a ground plane that's about 10 times larger. So we'll go for a height of 20, but now we can see this is not centered. So we're going to change our lower left Y coordinate to be -10, which gives us a nicely centered ground and microstrip line. So we can see these have now mapped to layers. So this is the equivalent of the schematic we've drawn, and we want to start our simulation. So for this, we will need ports. So I'm going to go back to layer 1, and I'm going to choose to add a pin. Keep in mind this is a pin and not a port, and that's quite important. So for now, we'll add 1 point at the input of our microstrip line. So you can see that's pin 1. Now, in order to add pin 2, I need a second pin to connect to the ground layer. So for this, I will change my layer to become layer 2. You can see the color has changed, and I'm just going to offset this by less than 1 millimeter to make it easier to see. So that's pin 1 and pin 2. I'm going to go ahead and do the same on the other side or the other end of the microstrip line. I'm going to add my port, my pin, and then I'm going to go and do the same for the ground plane. And now I'm going to save this. And what needs to be done at this stage is to start running a simulation. So for this, you can go into options or get into the electromagnetic or EM simulation settings. You'll need to create a new one because this is the first time you're running one in a workspace. So we'll create a new EM setup. We'll close the original dialog, and now you can see it's complaining about the substrate. There is no substrate defined, so we need to define a substrate. So we click new, we call it substrate. In terms of which template we need to use, so different templates, mostly aimed at semiconductors, so gallium arsenide or silicon, but we're going to choose a simple 2-layer FR4 substrate, which we're going to modify because we are not using FR4. So creating substrates, you'll see we've got a top conductor layer, which is mapped as a conductor. There's a middle conductor layer, which we don't have. That's not in the boards that you have in the labs. So what I'm going to do is I'm going to right click and unmap this layer. Now you can see there's a stack of 2 dielectrics, which means I need to get rid of one of them. So I'm going to delete the lower one along with its upper interface where there was a conductive layer. which now leaves us with a simple 2-layer board. Now I've got my top layer, which is a conductor, my bottom layer, which is another conductor, and these are not currently mapped to our layers. So from the names menu, I'm going to change it to be conductor 1 to match my layout, and I'm going to change this to be conductor 2 to match my layout. And I'm going to save this and go back and take a look at my layout. Just to double check the numbers are correct, so the conductor layers are correct. Now I can go into the substrate and start by defining my dielectric properties. Now here it says the material is FR4. We are not going to be using FR4, we're using a different dielectric. So what I will do is I will double click on the material properties. I will click on the additional menu, and now you can see here the library of existing dielectrics in Workspace. Immediately, you can't see the material that we're using, so you can go and add from your database. You've got a library of most common materials, including 3D printing filaments, substrates, PCBs, commercial materials, and also semiconductor substrates. So in order to try and find the materials I'm using, I'm going to sort by the dielectric constant. I know that I'm working with a dielectric constant of 2.94, so I'm going to assume that based on the tangent delta and the real permittivity, this is correct, but we can go ahead and adjust these, and I'm going to press OK. Now this is going to be my new material, so I'm going to go here and change that to be the material that I'm using. And I'm also going to change the thickness to be the thickness of the PCB that I have at hand. That's going to be 0.76 millimeter. I'm going to change the conductor thickness to be 35 microns. And I'm now going to save my substrate and close the substrate window. Back to the EM simulation menu, we can have a look at substrate. So it's now no errors. So what we need to do is to define simulation ports. Because we defined 4 pins, the simulator thinks that we're going to have 4 simulation ports, but what we have instead is a 2-port device. So what we're going to do is we're going to try and adjust this within the port menu. So we're going to open the port editor, and you can now see that we have got the ground layer being implicit. Now, this is not what we're doing here because we've already drawn the ground manually. So we do not want to implicit ground. We want to use an actual ground, which is going to be port 2. So we're effectively going to use the 2 ports as if they are a differential excitation to connect the ground to the second pin of our port. And we're going to do this across both ports. So remember, we've connected pin 1 and pin 2 to the input at port 1, ground and signal respectively. And then we're doing the same with ports 3 and 4 on the output. Now with the ports in place, we're going to close this, we're going to save it, and we're going to go back to our EM window. You can now see that there are no more errors. So one thing to look at is the frequency plan. So this is going to go from 0 to 10 gigahertz. I'm going to stop it at 5. It's going to do up to 50 frequency points, but it's going to interpolate the data in between them. So let's leave that the same as it is. Output plan is useful if you want to save currents or electric fields on your materials, or if you're simulating an antenna, you could save the radiation properties of your antenna. But for our simulation, we're going to keep this as it is. So it's not going to save any currents for now to simplify simulation and get it running quickly. We go back to the settings, you'll see that there are different modes. There's momentum RF, there's momentum microwave, which is used usually in higher frequency simulations. And then there's the most accurate simulator, which is the FEM or finite element method. If you want more information in these, just go into the help of ADS, which has a very nice analytical explanation on what each one of them does. We want to generate as parameters, we want the full solution of the problem. So now we just press simulate, and you're going to wait for a while because it's a layout simulation. You can see in the progress menu and the status message the number of frequencies you're cycling through. So if you reduce the number of frequency points you're simulating over, a frequency domain simulator like this will take less time. But for now, we'll work with 50 points. So you can see here, you've got a plot window which automatically populated with your S parameters data. You can see the discrete points and you can see the interpolated data between them. If we compare that to the previous menu, which is a simulation of your schematic, you will see that there's quite a high similarity, but there are also some differences. So if you look at the S21 data, previously we were getting an S21 for about -30. Now you can see that this degrades as you go higher in frequency, which is to be expected. And you can also see that the signal transmission has got some loss, even though previously the signal transmission did not have loss. So one of the things you'll be exploring in the lab is optimizing these parameters, and in future labs, modeling them in order to understand the loss sources, identify how to optimize these parameters, and you'll also compare these to measurements. Now, if you want to revisit any of your designs within your cells, you'll find the schematic, you'll find the layout, and that's it. Quick introduction to simulating circuits, both schematic and layout in ADS. And your next step will be to use the same windows to build equivalent circuits, to simulate more complex lines, and to compare that to the measurements in the lab.